Good afternoon. This is a quick little video on our next topic in thermochemistry, which is on Hess's Law, which we can find in Chapter 6 of Zoomdahl. First, let's discuss what a state function is. We talked about how a state function means that the value will always be the same regardless of the pathway. And we talked about this in class as an example of someone having to give money to someone else. If the first person were to give the money directly to the other person, that would what be called pathway 1 in the image below. But we can also give it to two other people who then turn around and give it to that same person, and we would call that pathway 2. We know that this is the same because the person has lost the same amount of money and the person has gained the same amount of money in both of these situations. But what if instead of people and money, we were talking about reactants, products, and so regardless of the pathway, in intermediate states, the enthalpy of two reactions will always be the same. That's the definition of a state function. Here's an example of that. We have A turning into B, and that's denoted by pathway 1, and it would have the enthalpy delta H sub 1. But then we also have pathway number 2, where A is turning into X, Y, and then B, and that's denoted as pathway number 2, and it would be given an enthalpy value of delta H sub 2. These two enthalpy values would be the same because the definition is going from a particular set of reactants, in this case A, to a particular set of products, in this case B. The change in enthalpy is the same if performed in one step, which is done in pathway 1, or if it's done in many steps, which is done in pathway. Now let's talk about Hess's law in a real-life example. The first reaction at top, nitrogen gas plus 2 moles of oxygen gas, gives us 2 moles of nitrogen dioxide gas. If you were to measure the enthalpy of this reaction, you would determine it to be 68 kilojoules. Now, below it are two reactions that could be applied one right after the other. And it would once again create nitrogen dioxide from 1 mole of nitrogen gas and 2 moles of oxygen gas. The first reaction has an enthalpy of 180 kilojoules, and the second has an enthalpy of negative 112 kilojoules. If we combine these reactions together, we would add the enthalpies together. The enthalpy of sequential reactions is the sum of those reactions, which creates 68 kilojoules of energy, aka 180 plus negative 112. We can look at the same exact reaction from a different diagram, a different perspective. This diagram is used in Zoomdahl very frequently, so you should familiarize yourself with it. On the left, reaction 1 is denoted from N2 and 2O2, that's your starting point, and the arrow up is showing that you had to add some sort of enthalpy, some sort of energy had to be introduced to the system in order to turn it into 2 moles of nitrogen dioxide gas. On the right-hand side, we see it as the two-step process from the previous slide. Nitrogen and oxygen gas combine together to create 2 moles of nitrogen monoxide, and that requires 180 kilojoules. When it's combined with another mole of oxygen gas, it releases 112 kilojoules, which would give us 2 moles of nitrogen dioxide. That difference is still 68 kilojoules. You can think about it like this. It's as if you were to go up 68 flights of stairs on the left-hand side. On the right-hand side, you went up 180 flights of stairs, but then down 112 flights of stairs. You're still on the same floor, 68, but the pathway that you got there were very different. The first one only required a one-step process of 68 kilojoules, and the second one required 2 steps, but still only a difference of 68 kilojoules. Sometimes, though, the reaction we're trying to calculate is not written exactly as we would like it, and I'll show you an example of that in a couple slides. But hypothetically, if we need to reverse a reaction, aka the reactants become the products and the products become the reactants, we would multiply that standard enthalpy by -1, and that's denoted in the diagram below on the left-hand side. Originally, we have A and B creating C, and that has an enthalpy of 150 kilojoules, but if we were to have C and turn that into A and B, the enthalpy of that reaction would be negative 115 kilojoules. However, when we need to double, triple, or multiply a reaction by a factor, we can multiply the reaction by that factor, the enthalpy of that reaction by that factor. So same reaction, A plus B gives us C, and again that has an enthalpy of 115 kilojoules in the diagram to the right. If we were to double that reaction, if we were to have 2 moles of A react with 2 moles of B, create 2 moles of C, that would release 230 kilojoules. That should make some intuitive sense. If we double the amount of reactants and double the amount of products we're going to make, we're going to double the amount of energy that's released from that reaction. If this is a little confusing, think back to your Algebra 1 classes when you have a system of equations. You might see a problem like this: 3x plus y equals 15 and 2x minus 3y equals 10. Your first step would be to multiply that top equation by 3, giving you 9x plus 3y equals 45. And then you would keep the bottom equation the same, 2x minus 3y equals 10. You then combine them and you could solve for x, which in this case equals 5. So similarly, we can modify, reverse, or multiply a reaction by a factor, and we'd have to multiply that enthalpy by the same thing. So just like combining equations, we can multiply them by a factor, reverse them, aka multiply them by 1. So just like you solve system of equations back in algebra class, solving Hess's law problems will be very similar to that. So let's take a look at an example of one. Here is an example of a Hess's law problem. Here we have carbon disulfide reacting with 3 moles of oxygen gas to create carbon dioxide and 2 moles of sulfur dioxide. Now, if you were to look up in the book, you would only find the enthalpies for the following reactions: carbon reacting with oxygen gas, sulfur reacting with oxygen gas, and carbon reacting with sulfur gas. And you might ask yourself, well, how on earth, Mr. Killian, am I supposed to calculate the delta H of that reaction? Because if you'll note, none of those reactions have copper disulfide as a reactant, as that first reaction in blue does. Well, that'll be our first step. Let's reverse that first reaction. So here I've taken copper disulfide, that third reaction, and I've flipped it. You'll notice my delta H has also changed to negative 87.9 kilojoules. Remember, when we flip a reaction, we have to switch the sign of that. And the second thing we're going to do is we're going to double that second reaction, because if you'll note, we're only making 1 mole of sulfur dioxide, but we need to be making 2 moles of sulfur dioxide. So we need to double that reaction. Well, if we double the reaction, we have to double the amount of enthalpy that would be released or absorbed. So negative 296.8 kilojoules becomes negative 593.6 kilojoules. Fortunately for us, we don't have to do anything to that first equation we see. Copper plus oxygen gas gives us copper dioxide. We can leave that alone. Now, when we combine all of these, we see that we get the same exact reaction as the top. Copper disulfide reacts with, carbon disulfide reacts with oxygen gas to create carbon dioxide and sulfur dioxide, 2 moles of sulfur dioxide. We would add those three values, negative 87.9, negative 593.6, and negative 393.5, and we get negative 1,075 kilojoules per mole. The reaction that we calculated, even though it took 3 steps, has the same reactants and products as that first reaction. So by the definition of a state function, we can confidently say that the enthalpy of this reaction would be negative 1,075 kilojoules per mole.